Alright, welcome back, physics students. This is the last example for projectile motion for chapter 3, which we would have done on Friday if that guy didn't go all Grand Theft Auto. Alright, so now, we're going to be doing cliff to ground projectiles. Now, before we look at cliff to ground, let's look at ground to ground again. So ground to ground projectiles are going to be a symmetric path, ground to ground. And ground to ground, again, has some special characteristics. The initial speed is the same as the final speed. The initial y naught is the same as the final y, vy. So the initial vy naught is the same as the final vy. And the projectile starts and ends at the same location in the y direction. And so if you're doing ground to ground, remember you're just modeling as somebody throwing a ball up and catching it at the same location. But for cliff to ground, what we're actually going to do is we're going to actually go up here, and I'm going to start the analysis here. And so instead of starting at the ground, I'm going to start at some point on the path. So kind of pretend I draw a cliff right here. So this is actually my initial position, 0. And the rest of the projectile is kind of like it would be for the rest of the ground to ground, except I'm just kind of starting the analysis at that point. So if I go down here and I start this at point 0, then if I do a cliff to ground launch, then it's going to continue on that path. But for cliff to ground's a little bit more confusing. But let's put some numbers in. So I'm going to have the same initial velocity and angle that I did in the last problem, although I'm starting from the cliff, so be careful. So let's call this cliff height 18.0 meters. Alright, so let's say I have initial velocity, or initial speed, I should say, of 20.0 meters per second. And my initial angle, let's say, is 60.0 degrees. Okay, remember, the first thing I want to do here is find my Vx and my Vy. I'm going to extend this up so I can draw a Vy. So my Vx is going to be the 20 times, Vx is the adjacent angle in this case, so times cosine of 60. And so that's going to be, like it was in the last example, plus 10 meters per second. And then Vy is going, this is Vy naught, is going to be 20 times sine of 60, which is plus 17.3 meters per second. Alright, so if we assume that there's no resistance and this is 2D, then the Vx, the component of velocity in the x direction remains constant, and Vy is variable as a result of gravity. Now, if we want to model this, the y direction, as a 1D direction problem, you can kind of picture a person over here throwing a ball straight up at Vy naught is equal to plus 17.3 meters per second. And as you remember from chapter 2, if the person throws the ball straight up, it's going to rise upward, reach a velocity of 0, and then fall back down the cliff. So what's cool here is that if I trace a line over, both balls would go the same height, as long as the person throwing the ball throws it at the same Vy naught, the plus 17.3. If this person were to throw it the same speed as the ball, the 20.0 meters would actually go higher. So as long as the y components are the same, then this is a perfect analogy between the two. Okay, so the first thing I want to do with this problem is I want to find the height, the maximum height, so part A. I want to find the maximum height off the ground that the ball goes. So max height, so you have to be careful here, height off the ground. Okay, so I'm going to redraw this. Okay, so this distance here is 18 meters. And so I want to figure out what this capital H is, the maximum height off the ground. Alright, well, if I model this, the y direction, as a person throwing a ball up at the same initial speed, and then it comes back down, then this little piece in here is little h. And this little piece here to the top is little h. And so my big H is going to be equal to 18 meters, the height of the cliff, plus the little h, which is the height that the ball goes if the person throws it up, and that Vy naught is plus 17.3 meters per second. So I can just model this as a person throwing a ball straight up to point 1, so I'll call this the top point 1, where Vy1 is equal to 0. And I'm only concerned about the y direction. So I'm going to actually use equation number 3. So I've got Vy1 squared is equal to Vy naught squared plus 2ay times delta y. Now, if I put the coordinate system on my ball, so over here on this drawing, here's x and y, so I'm putting my coordinate system at the initial position, then if I do that, then my delta y is just my little h. So it's not the height off the ground, it's the height the ball rises relative to where it was thrown. And then ay is going to be minus g. And then vy1 at the top is 0. So this is very similar to the last problem, where I find that h is equal to Vy naught squared over 2g. So that's Vy naught is plus 17.3 meters per second squared, 17.3 meters per second quantity squared, divided by 2 times 9.8 meters per second squared. And so my little h is equal to plus 15.3 meters. Now again, if you look up at the drawing, this height that I calculated is just the height from where it was thrown to where it goes to its maximum height. So if I want the height off the ground, I'm going to have to add this 18 to this number. So big H is equal to 18 meters, the height of the cliff, plus little h is how high it went once the person threw it. So 18 plus 15.3 is going to be equal to 33.3 with sig figs. So big H is 33.3 meters. Okay, cool. All right, next. I want to find, part B, the total time in the air. So I'm going to redraw this problem again. Cliff is 18 meters, 18.0 meters, and so the ball is launched. And assuming that we have no air resistance and it's 2D, then the x direction is constant, and the total time in air is actually dictated by the y direction. So if I model this as a person throwing a ball upward at Vy naught is equal to plus 17.3 meters per second, then we know how to do this from chapter 2. The ball goes straight up and comes straight down. So my initial position is 0, and my final position I'll call 2. And remember, in order to solve this, we had to use the quadratic formula. So I'm just going to look at the y direction, because the y direction is dictating the time. And I'm going to go from 0 to 2. So y2 is equal to 1/2 ay times time 2, which is what I'm looking for, squared, plus Vy naught times time 2 plus y naught. And remember, I'm putting my coordinate system on my ball. So y naught is 0. Let's see, ay is minus g. Be careful, Vy naught here in the middle is not 0. And y2 is going to be actually negative 18 if I put my negative 18 meters if I put my coordinate system on the ball. And so let's see, 1/2 times minus g is going to be minus 4.9. Vy naught is plus 17.3. And you can set this up however you want to. You just have to set this equation equal to 0. I prefer not having a negative leading term. So I'm going to bring this whole right-hand side over to the left-hand side. And if I do so, then I'm going to get 4.9 t squared, and then minus 17.3 times t, and these are actually t2s, and then minus 18.0, and that's equal to 0. All right, so just be careful with your signs on this. So I'm going to put this into my calculator and find the zeros, just like I did in chapter 2. And remember, you're going to get one negative time, and the negative time actually comes about mathematically because the negative time would be where the time the ball actually started down here if it were a complete ground-to-ground projectile. So that's the time t minus where you're at here. So I only want the positive solution. And if I put this into the calculator, for this particular case, I get my T2 is equal to 4.37 seconds. And that's it. Okay, the next thing I want to find, part C, I can still do it on this page, is I want to find the distance from the base of the cliff to point 2. So basically I'm looking for the max range. Alright, so if we go back up to our drawing, and I'll do this in pink, this is my maximum range R from the base of the cliff. Now, remember the x direction, and the x component is a constant 10 meters per second. So this ball is just traveling at a constant 10 meters per second all along its path. So for the range, I could just model this as a car traveling at 10 meters per second for the total amount of time that the ball is traveling, which is 4.3 seconds. So this is actually relatively easy once you find the time. So I'm going to use the equation for constant velocity. So Vx is equal to delta x over delta t. And in this case, I'm concerned with going from 0 to 2. So my delta x is going to be equal to my rate in the x direction times the time, which is actually my t2. And so this is going to be equal to plus 10 meters per second times the total time. So my range in this case is going to be 43.7 meters. Okay, and then the last thing I want to do in this example, and part D, is I want to find the velocity at impact. Okay, this is actually just a little bit trickier than ground to ground, and here's why. If I do cliff to ground, my takeoff speed here was 20 meters per second at an angle of 60 degrees here at the original point 0. And my Vy component was plus 17.3 and my Vx is 10. Well, if I go straight, this is really kind of cool. If you go straight across here, then at this particular point that's straight across from the cliff, I know the speed's actually right here. The speed's going to be 20 because it's the same. This is like a ground-to-ground launch, and the angle is going to be minus 60. But the ball continues to fall further, and so down here the speed actually has to be above 20, and we would expect a steeper angle since it's still falling. And so to find the velocity impact, I'm going to have to find my. This is point 2. I'm going to have to find my. This is point 2. I'm going to have to find my velocity Vy2 here. And Vy2 is not equal to negative, what it was at the beginning, 17, because it's fallen further than ground to ground. And my Vx, in this case, is still going to be 10, because we're neglecting air resistance, so my Vx is constant. And so here's the magnitude of my velocity or my speed, and then here's my angle theta 2. Okay, so what we need to do is find V2. So I'm going to go from 0 to 2. And because we have the total time, it makes the problem easy. I mean, with any of these problems, if you've got the time, you can just use y direction to find out. You can use equation number 1 to find out the y direction. So I'm going to use velocity. So I'm going to use the first equation. So Vy2 is equal to Ay times T2. Plus Vy naught, and Ay is minus g, so that's minus 9.8 meters per second squared, times the total time, which we found before to be, using the calculator, 4.37 seconds, plus my initial velocity in the y direction, which was plus 17.3 meters per second. And so my Vy2 is going to be equal to a negative 25.5 meters per second. Okay, now we're not done, and this is where students commonly make mistakes when asked for the speed or the velocity, because this is just the y component of velocity at 2. In order to find the speed, I need to use the Pythagorean theorem with Vx. All right, so the first thing I'm going to do is I'm going to find the speed at 2. So the speed at 2 is going to be the square root of Vx squared plus Vy2 squared. And if I do this, I'm going to get the square root of the quantity 10 squared plus this minus 25.5 squared. And if I put that in, then my speed is 27.4 meters per second. Now notice that the initial speed was 20, and if I did a ground-to-ground launch, which would be at this point here, the speed at this point, you can call it 0.3 if you want, is in fact 20 meters per second. But the thing is the ball keeps falling and keeps accelerating due to gravity, so it accelerates further, and the speed of impact is 27.4 meters per second. And then the last thing I need to do to get velocity is I need my angle. So theta 2 is equal to inverse tangent of Vy2 over Vx, which is inverse tangent of Vy is minus 25.5 meters per second divided by Vx, which is 10. And so my angle is minus 68.6 degrees. So I can communicate my velocity at impact is going to be a speed of 27.4 meters per second, comma, the angle at impact is minus 68.6 degrees. And let's go back up and look at the drawing real quick. So again here, initial speed is 20, goes to a speed of 0, back to a speed of 20, continues to accelerate with gravity. So the speed here, this, which is the resultant vector, is 27.4. And then the angle of launch is 60. And straight across, I know the angle here would be minus 60, but as the ball continues to fall, the angle becomes a little steeper, and so this angle, theta 2, the angle of impact, is minus 68.6, which we found down here. And so that's how you do cliff to ground. All right, cool. All right, I'll see you guys tomorrow and answering questions. All right, have a great rest of the weekend. Have a good one.